The Quadripartite Cold Phase Refinement System, Lecture in Applied Electro-Hydrometallurgical Methodology. The Anthony Thomas System, colloquially called the Lecture in Applied Electro-Hydrometallurgical Methodology. The Anthony Thomas System, colloquially called the Four Horsemen, represents a cold-phase, multi-cell electrochemical method for silver refining and general mixed metal purification. It operates within a doctrine of patience, transparency, and reproducibility. Its architecture, 4 glass vessels connected only by occasional transfer of liquor or common electrode conductors, illustrates the dynamics of controlled oxidation, displacement, and deposition without recourse to distillation, filtration, or thermal drive. Its foundation is the principle that copper chemistry and slow ion exchange can form the entire scaffolding of noble metal recovery when guided by measured current, stable pH, and time. Section 1. Physical framework. The process requires 4 unheated glass jars, arranged linearly but electrically linked through copper conductors or shared electrolyte bridges. Each jar carries both independence and dependence. Independence in chemical environment, dependence in ionic communication. All reactions occur at or below ambient temperature. 1. Vessel wine. Primary dissolution cell contains dilute nitric or mixed nitrate phosphate acid seeded with copper metal or copper nitrate. Silver-plated or mixed scrap enters here. The active copper dissolves selectively, giving nitrate ions access to base metal layers and liberating silver as suspended chloride if gentle chloride presence is maintained. This stage defines oxidation power. 2. Vessel 2. Transitional sulfate cell receives decanted liquor containing Cu2+, NO3, PO43, and trace agios. Introduced to a prepared copper sulfate medium, this cell slows reaction kinetics. The 2 ionic populations meet under mild potential, allowing spontaneous cementation. More noble species, primarily silver, begin plating on copper cathodic surfaces as a soft metallic haze. This is the principal extraction stage for silver. 3. Vessel 3, electrorefinement cell. A copper anode and cathode pair submerged in balanced QSO4Q NO322 solution. Controlled current at fractional ampere levels draws pure copper onto the cathode while insoluble residues, slime, rich in silver chloride, gold dust, and minor lead or tin oxides, settle beneath. The current is constant, not pulsed, to avoid dendritic formation. 4. Vessel 4, a passive crystallization and neutralization. Cell functions as the recovery terminus. The electrolyte rejected from the 3rd jar is left to solar evaporation or cool condensation cycles. Copper sulfate crystallizes in geometric blue masses, visually signaling completion. Remaining liquor is weakly acidic and can be neutralized or recycled. In this architecture, each jar mirrors a natural stage in metallic transformation: dissolution, displacement, deposition, rest. Section 2. Chemical and electrochemical dynamics. At the molecular level, the process expresses the hierarchy of electrode potentials. Cu, Ag, Au. By mobilizing copper as both reagent and conductor, the system achieves displacement refining. Copper willingly surrenders electrons, dissolving as Cu2+, and forcing silver out as neutral atom. In vessel 1, oxidation initiates. Cu plus 2. HNO3. CuNO3. 2 plus 2H. Plus 2E. The released electrons migrate through solution or wire to reduce silver ions. 2Ag plus 2E. 2Ag. The bath darkens blue. Silver films deposit invisibly on submerged surfaces. The phosphate buffer prevents violent fuming. Chloride traces fix silver into crystalline aggregates rather than colloidal suspension. In vessel 2, Cu2+ concentration rises, nitrate falls, sulfate becomes dominant. Reduction proceeds by direct contact cementation. Cu plus 2Ag was. Cu2 plus 2 Ag. No external power is required. Product appears as silver flake or powder. In vessel 3, applied current sharpens selectivity. The anode dissolves to feed copper ions. The cathode plates them in pure metallic form. Insoluble compounds of less active metals accumulate as mud, so-called anode slime, containing AO, AgCl, and remnants of tellurides in trace e-waste scenarios. In vessel 4, ionic strength declines naturally. As evaporation proceeds, crystalline CuSO4, or mixed double salts, form.
Lecture: The Quadripartite Cold Phase System, an extended recomposition in the tone of a university colloquium for the blind and the attentive listener. Prologue: The Nature of Metal and Time. This lecture addresses the so-called Anthony Thomas Quadripartite Cold Phase Refinement System, often referred to in less formal commentary as the Four Horsemen. Regardless of the theatrical title, the content belongs to a quiet and slow branch of applied electrohydrometallurgy that dispenses with heat, speed, and the trappings of industrial volume. It functions under ambient temperature, glass containment, and deliberate temporal extension. Its chief concern is the behavior of metallic ions, chiefly copper, silver, and traces of gold, under minimal potential difference and restrained chemical drive. Our discussion proceeds from first principles: the recognition that a metallic element subjected to an ionic medium may transfer charge without violence. That equilibrium between dissolution and deposition can be maintained as a steady conversational rhythm, not as competition. This process, viewed scientifically, exhibits orderly electron motion. Viewed philosophically, it demonstrates patience organized into molecular evidence. Part 1: The Conceptual and Physical Framework. The quadripartite system employs 4 glass vessels. They are not symbolic, they are functional separations of electrochemical stages. Each vessel is autonomous in its fluid identity, yet dynamically linked by occasional decantation or shared electrical continuity. The vessels stand arranged linearly to express progression. Jar 1 begins the transformation, Jar 4 concludes it. No heat is added, and no pressure is induced. Every effect arises from potential difference, ion mobility, and natural evaporation. Vessel 1, Primary Dissolution Cell. The first jar contains a mild laboratory mixture of nitric acid and phosphate buffer, initiated with small copper metal fragments, or prepared copper nitrate. When composite scrap or silver-plated material is introduced, copper initiates oxidation, sacrificing itself to nitration, while silver remains insoluble, forming suspended chloride under slight halide presence. The purpose of chloride inclusion is restraint. It arrests runaway silver dissolution, holding it in a visible particulate state. The electrolyte thus turns blue as copper ions saturate the liquid, signifying both oxidation activity and electrical readiness for later stages. Hydrogen evolution is negligible if the potential is kept below 1 volt direct current. Any visible bubbling indicates excess and must be reduced. Vessel 2, Transitional Sulfate Cell. The second vessel receives liquor from the first after particulate settling. Here, copper sulfate replaces nitrate dominance. This ionic shift alters kinetics dramatically. Reaction speed drops, selectivity improves, and displacement occurs by direct contact rather than by current. The copper surfaces within this medium host cementation, an ancient metallurgical phenomenon where a less noble metal dissolves and a more noble one appears upon it as a film or flake. Silver ions reduced to elemental silver coat the copper gently, leaving base ions adrift. No apparatus of agitation is needed. The gravity-fed serenity of the jar provides uniformity. Vessel 3, Electro-Refinement Cell. The third stage establishes a controlled electrical field. 2 copper electrodes, 1 sacrificial anode, 1 receptive cathode, stand immersed in a balanced solution of copper sulfate and copper nitrate. Direct current at fractional amperage drives the refinement. The cathode accrues dense, pure copper metal, while insoluble residue, NOD slime, collects beneath. This residue contains noble metals in minor proportion: silver chloride, granular gold, and oxide traces of lead and tin originating from the initial feed. The current is stabilized to prevent dendritic growth, ensuring crystalline coherency. Over time, the liquor assumes transparency, reflecting purification and depletion. Vessel 4, passive crystallization and recovery cell. The last jar is passive by design. It receives the decanted remainder from the third vessel. The electrolyte slowly surrenders water to ambient air. Dissolved salts reduce their solubility and deposit as copper sulfate crystals, readily identified by deep azure geometry. No intervention beyond patience is required. The remaining weak acid solution can be neutralized with carbonate, producing harmless sulfate salts fit for secondary extraction of zinc, nickel, or iron by simple precipitation. 4 jars, therefore, correspond to 4 philosophies of transformation. 1. Dissolution. 2. Displacement. 3. Directed refinement. 4. Rest and crystallization. This is chemistry rendered as narrative sequence, yet unembellished by metaphor. It is plain matter-changing state through ordered discipline. Part 2. The electrochemical logic. Metallic exchange follows the numerical lineage of electrode potentials. In standard aqueous systems, copper possesses a lower reduction potential relative to silver and gold. Consequently, copper surrenders electrons, dissolving as divalent cation Cu2+, while silver and gold absorb those electrons, converting from ionic to metallic form. In quantitative terms, the half reactions stand as follows: oxidation, copper to copper ions plus 2 electrons. Reduction, silver ions accept those electrons to become metallic silver. This is not symbolic language. It is the electron ledger of existence. The reaction balance, unheated, stabilizes itself without vapor or fume. With phosphate buffer maintaining pH within gentle limits, nitric concentration never escalates to gas evolution. The system embodies thermodynamic moderation. No explosion, no frenzy, merely continuous recalibration towards equilibrium. When this principle operates within the second vessel, an even purer demonstration occurs. Contact reduction without external circuitry. Copper metal immersed in copper sulfate solution containing trace noble ions will automatically yield part of itself to electron transfer. The noble species deposit, copper dissolves. The event requires nothing but immersion and time. By the third vessel, the manual electrical field substitutes for spontaneous exchange, thereby imposing human control. The operator determines rate through amperage, not through temperature. Oxygen evolution remains minimal. Hydrogen nearly non-existent. Every deposited lattice of metallic copper represents not mechanical work, but the visible fingerprint of electrons settling into new coordination. Evaporation in the fourth jar serves not as loss, but as declaration of finality. As the blue deepens to stillness, copper sulfate reasserts its crystalline order, marking completion. Each crystal encodes the slow arithmetic of the previous stages. Part 3. Operational ethics and the philosophy of slowness. Anthony Thomas articulated in Minimal Surviving Notes that haste in chemistry is a form of ignorance. Every dissolution performed below its boiling limit preserves structure. Every reaction coaxed rather than provoked minimizes waste. The practitioner observes that time in chemical systems becomes a reagent as real as acid or salt. In such practice, clarity equals success. Cloudiness indicates suspended error, unreacted material, unstable intermediate, or unfiltered precipitate. True progress is shown by transparency and the absence of smell. Transfer between jars occurs by gravity alone to eliminate mechanical disturbance. The entire operation becomes a study in non-force. The energy economy is exact, 1 volt per jar at most, often less, producing refinement worthy of higher voltage, yet generating no audible or visible violence. From a wider philosophical view, this cold phase operation mirrors intellectual discipline itself. The refusal to accelerate stands as defense against entropy of thought. To maintain patience within an experimental series is to align methodology with the behavior of light in still water, refracted but unbroken. Part 4. Product sequence and analytical yield. Upon completion of one full cycle, the system yields measurable and separable phases. 1. Copper phase. Predominant metal recovered, refined to near theoretical purity. The metal appears as coherent plating or foil on the cathode, its color bright reddish pink, free of black oxide. 2. Silver phase. Emerges as flake or fine granular mass, often initially bound in chloride matrix. Gentle reduction by carbohydrate solutions such as glucose or by ascorbate derivatives transitions it to metallic condition without high temperature. The product may be washed, dried, and compressed. 3. Gold phase. Persists within the anode residue from the third vessel. Owing to its minimal concentration, it is collected not by chemical reaction, but by mechanical segregation, centrifugation, or sediment isolation. Its particles resist dissolution entirely within the sulfate environment. 4. Residual phase. Constituents of nickel, zinc, iron, lead, and tin manifest as secondary sulfate or oxide precipitates. Added carbonate neutralizes residual acidity and precipitates these as basic salts ready for further metallurgical recycling. Through this series, the system reproduces industrial electro-refining chemistry on laboratory scale without steam, agitation, or emission. The real innovation does not lie in novel reagents, but in the equivalence of observation and control. Part 5. Relation to broader hydrometallurgical traditions. Traditional hot acid refining seeks rapid dissolution followed by rapid precipitation, valuing throughput above precision. The quadripartite system replaces heat with patience, viscosity with gravity, and oxidizing excess with measured potential. Each of these substitutions carries philosophical consequence. Where industrial chemistry burns, this method listens. Where factory columns bubble, glass cylinders rest unmoving. Yet both obey the same underlying formalism of electron donation and reception. If described for pedagogical emphasis, the 4 vessels provide live demonstration of sequential potential gradients, each jar representing a smaller step along Gibbs free energy descent. Differential solubility as a functional selection tool rather than mere side effect. The dynamic balance between an open system, evaporative, and a closed system, electrolytic. Sustainability achieved not by external virtue, but by intrinsic kinetic self-limitation. To the philosophical reader, this arrangement expresses the axiom that the measure of purity corresponds to the measure of restraint. To the chemist, it expresses conservation of energy and minimal side reaction. To the blind practitioner listening here, consider each jar not as visual spectacle, but as timed voice. The first jar murmuring rapid solution, the second whispering gradual substitution, the third humming steady current, the fourth silent crystallization. Sound and time themselves replace color as analytic instrument. Part 6. Educational and experimental implications. The quadripartite system serves as model experiment for undergraduate demonstration or personal study into redox sequence stability. Its safety profile, due to absence of boiling, pressure, or halogen gases, allows use in small rooms without fume extraction. Conductivity measurements furnish quantitative tracking of reaction progress for those lacking visual markers. Measuring current drop across fixed resistors establishes the same data that a sighted observer reads through color intensity. It also bridges disciplines. Chemically, it lies within hydrometallurgy. Electrically, within electrochemistry. Pedagogically, within philosophy of science. For it demonstrates that measured patience yields empirical fact. The moralizing overtones of slow science are irrelevant. What matters is that the kinetic curve flattens enough for comprehension. Slowness converts observation into education. Part 7. Concluding analysis. The Anthony Thomas quadripartite cold phase refinement system crystallizes a convergence between metallurgical accuracy and philosophical moderation. Its 4 glass vessels function as open textbooks where electrons write their record for those who listen rather than watch. Copper, silver, and gold behave not as precious commodities, but as agents of demonstration that chemical hierarchy is immutable and intelligible. Every dissolution is balanced by emergence elsewhere, every departure by arrival, every ion replaced by another's willingness to move. This is the intellectual value of the so-called Four Horsemen. It transforms metal into narrative without inventing myth. It redefines economy, not the economy of finance, but the economy of energy and material. It reasserts that precision is achieved not through enhancement of force, but through reduction of noise. To conclude in plain chemical language, under controlled low-voltage conditions, copper nitrate and copper sulfate together mediate the transfer of charge sufficient to displace silver and, incidentally, free gold. The environment remains oxygen stable, thermally neutral, and indefinitely repeatable with replenishment of electrolyte. In its completeness, the system is both laboratory miniature and philosophical diagram of measured change. Listeners and practitioners who carry forward this work should hold one understanding constant. Metal obeys potential, potential obeys time, and time obeys nothing but itself. End of lecture.